So welcome everybody. My name is Laurel Glenn. If you've been to one of these safety webinars the last 2 months, you might recognize me. I'm the program manager for safety. We appreciate you joining the webinar today that we have. It's about the usage of 5G technologies and video analytics in order to enable safety communications between pedestrians and vehicles, specifically at system intersections. So you've all entered this meeting muted. I'm going to ask that you stay muted until the question and answer session. I'm going to try again to enable captions so they can be on for your convenience. And then if you have any questions during this webinar, you can go ahead and enter them in the chat box. We will get to them, or if they're, if we can't interject, we'll go ahead and interject where we can to ask those. Also, you can use that chat box. Feel free to drop things, usually when conversations get started. If there's any kind of resources that you're looking for or that you might have that you want to share, go ahead and use that chat box down at the bottom as well. All right, so I'd like to first go ahead and introduce the presenters. We have Jean-Paul Talledo, who is an assistant research scientist and senior technology implementer at the Virginia Tech Transportation Institute. What does that mean? It means he designs, develops, and integrates technologies for automotive research, including ADAS platforms, V2X and 5G communications, computer vision, and algorithm development for autonomous and connected vehicles and work zone safety. We also have Marty Miller, who is also from the Virginia Tech Transportation Institute. Marty Miller is a Berea College graduate and a research associate in his 9th year here at VTTI. And his work largely focuses on safety and human factors assessments of ADAS and other advanced vehicle features. So he's involved in the design process of experiments. He does hardware, software development, performs data collection, and analyzes the data to evaluate how real humans interact with prototype systems. So I'm going to go ahead and turn things over to Marty to begin our presentation.
All right. Can everybody hear me okay? Still good? All right, great. So yeah, like Laurel said, we're here to talk about private 5G technology implementation and testing at the VTTI Smart Roads. This was safety funded, obviously, here for the safety webinar. Like she said, I'm Marty Miller, and I'll just kind of walk through some of the background of what we're going to be doing or what we did, and then we'll get to some results here after a while. All right, so as pretty much everyone here is probably familiar with, pedestrian or general fatality, transportation fatalities in the United States have been growing since 2020, an all-time high last year, according to preliminary data. This also means that there have been an increased number of pedestrian and cyclist fatalities, at least starting in 2018, that's been rising. And the most recent data suggests about 8,000 people, pedestrian and cyclists account for about 8,000 or almost 20% of all fatalities in the United States. Yeah, that's 2018 data. 2019 data suggests that upwards of 10,180 fatalities happen at intersections. And like I said, this has been a growing trend over the last several years. So basically, this project was looking to explore how new intersection infrastructure, like 5G and C-V2X technologies, could be leveraged to hopefully provide safety alerts to pedestrians and drivers alike. So, and we'll get into all the details about what specifically that means, but that's the general idea. So our methods generally looked like this. So first we installed some private 5G equipment, including a camera and an edge computing some cameras and an edge computing platform. This was, the 5G equipment is specifically used here because it's designed for ultra low latency communications that would be suitable for these type of safety critical alerts that we were exploring for this study. We did system calibration and did some machine learning model validation on the equipment after it was all set up. And then we developed some HMIs for pedestrians and vehicles to make use of alert capabilities of the private 5G deployment that we had. Last thing we did was we did some scenario testing to evaluate the accuracy and the total system latency from when the actual event was detected to when the alert would be presented to either the pedestrian or the driver. And we'll talk about all that towards the end. All right, JP, do you want to talk about the actual system development?
Sure. Good afternoon, everybody. And I'm going to go through the prior 5G system development that we installed here at BTTI. Next slide. The sponsor, which is NIC, worked with BTTI to actually design and deploy a private 5G network, taking advantage that BTTI has a CBRS frequency spectrum allocated here in Blacksburg and in Montgomery County. So that allows us to use the CBRS band to actually take advantage of ultra low latency communications by this private 5G network. The main components are shown here in this diagram, which are pretty much is the sensor source, which is our HD cameras. They are connected to some PC boxes or edge computing systems. They are actually doing all the video analytics. And that part of the video analytics is also transferred using a 5G link and fiber to the data center at BTTI, where a MEC server is actually running additional computations and the private 5G implementation is residing. All the CU, DU, and RU, which are terms for 5G, I'm going to describe. The RU is the radio unit. The radio unit is the one that connects to UEs, user equipments, and establish that wireless private 5G communication. That UE is like your phone. It's a device with a SIM card. They actually register in this private 5G network, and the RU connects to the CU and DU, which are control units, and provides all the implementation of a private 5G. Part of that system in the same network is the MEC, which allows us to do the video analytics on generating the alerts and triggers. They will be notifying back to the pedestrians or vehicles using the CV2X infrastructure the BTTI has here on the smart road. The 5G core, which is pretty much the authentication, validation of users, is actually running on a Amazon AWS instance, and that's actually through the internet. But I can say 90% of the equipment was deployed here at BTTI, and using the capabilities and low latency of fiber between the smart road traffic intersection and BTTI data center, we make it possible to reach pretty fast speeds and also data transmission between the edge computing or PC box up to the MEC server. BTTI also work on how this CV2X infrastructure can reach vehicles and pedestrians. We install some devices that we're going to discuss later on to alert the drivers and pedestrians when they are actually interacting within the intersection. Next slide, please. So the private 5G hardware, here you can see that we put different cameras. The interior cameras, they have some field of view shown in red. That's one of the sides of the camera. It's actually targeting and trying to detect road users within the intersection. But we also have cameras looking at a traffic incoming to the intersection that is shown on the green area. So there's 2 poles, vertical poles at the intersection here at BTTI Smart Road, and we put 2 cameras per pole. So that allows us to monitor pretty much a 360 environment at the intersection. We can detect road users coming to the intersection and also within the intersection. We work with a partner, with NIC, to actually understand the angles and also the tilt of each of the cameras to optimize the detection and perception during the video analytics. These cameras are normally IP cameras. They normally provide video stream over Ethernet, and they have HD and 4K capabilities. In this deployment, we only use HD quality due to also the video analytics performance based on the GPUs boxes that we installed in this deployment. Cameras, just to mention, has up to 150 meters range in terms of detecting road users, vehicles, SUVs, motorcycles, bikes, and pedestrians. So we do some calibration that we are going to discuss later on at different ranges. But pretty much our critical range was between 20 and 60 meters. Next, please. Part of the team here in VTTI designed some mounts for the RU unit. These devices, and they came here to VTTI, provides all the private 5G provisioning and transmission. And however, the sponsor couldn't design the entire adapters and brackets. So we have an effort to mount these at the smart road. As shown in the next slide, you can see some pictures during the installation of this RU unit. And that is one of the main devices that is actually providing the provisioning of the 5G network here at the VTTI Smart Road. All these devices, the 5G UE and RUs, are actually connected and linked to our VTTI data center using fiber. Next slide. The current implementation, which is a proof of concept, uses an independent GPU box, which is the blue boxes in the middle figure. Those boxes will receive the camera video stream in real time and adds and runs the video analytics. They are actually forwarded to the MEC at the VTTI data center. In order to house all the equipment of PC boxes, routers, power supplies, the mechanical team design and find the proper enclosures to house all this equipment. It was a little challenging due to the heat generation of all this equipment to maintain a waterproofing enclosure without fans, but we were able to actually control that by different aspects. But the main thing here is that we installed a PC box per camera to run video analytics, and also a UE or radio that connects these PC boxes to the private 5G network. We provide also remote access to these computers using our fiber link, but that was kind of a management procurement to allow the NIC team from Japan to be able to access remotely these computers and diagnostic any issues during the test. You can see here pictures of the instrumentation at the smart road. The first one is the two cameras. One is looking inside the traffic intersection. The other one is looking to the exterior. In the center, you see the three enclosures. The top enclosure has the UE radio. The center has PoE adapters for the cameras, or power supplies to power the cameras and provide Ethernet access to the bottom enclosure, which are the PC boxes running the video, part of the video analytics software. On the right, you can see there is also a CV2X RSU, part of the VTTI infrastructure, and that is the radio that uses CV2X to connect to the vehicles and the HMI elements that we designed for this project to alert pedestrians and vehicles as well when they have an alert or a threat scenario that we will describe later on. Next slide, please. So just a little bit of details of what I mentioned about the CBRS usage. Here is more in details of the spectrum. We actually request a FCC experiment approval that allow us to actually run this 5G infrastructure here at DTTI at the Smart Road. Even if we have CBRS, under CBRS, currently in US, you need to be SAS compliant. SAS means that every single unit needs to check if the part of the spectrum is allocated or is actually used by any priority channel allocation devices, which, for example, could be emergency vehicles or emergency systems. They actually need to take advantage of this spectrum. However, we got, due to the range and also the radius of this deployment, we were able to allocate a fixed spectrum frequency for 6 months in terms of between the 3.4 and the 3.5 gigahertz band, and they allow us to continuously test and deploy the private 5G. Next slide, please. Well, I will let Marty to go through the system calibration. The mostly for the cameras installed here on the Smart Road intersection.
Right. So the system calibration basically consisted of a series of boxes placed onto the roadway with colored tape on the edges of the boxes. And then basically we recorded a small video from each camera with all the boxes in the field of view. And then we had an additional LiDAR unit on the ground looking out at the boxes to with a known distance between the LiDAR unit and the camera itself. And that way we can, localize or have a ground truth positioning relative to the camera view with the LiDAR unit. So then this is used after the fact, and actually NEC did the work of actually taking all that data and creating a transformation between the camera view and the real world view for accurate positioning of vehicles and pedestrians that were detected in the camera view. Let's see. And I can talk about the HMI and the safety alert development. So the first thing we developed was a pedestrian lighting board. The system is capable of identifying potential collisions, particularly with pedestrians and vehicles. So we developed an HMI to alert pedestrians when this threat situation was detected. So we went with a ground-mounted lighting board with the idea of kind of as people are on their phones walking through intersections, maybe they don't notice that the light or the walk sign has changed. And this gives an option, might be more visually arresting than something mounted up higher. This also included a speaker for auditory alerts in case, it didn't get enough of their attention as is. And this all used CVDX OBU to process messages that were broadcast from the RSU network. So essentially how it worked is the camera would detect the collision. It would then transfer that information via the 5G network between the lighting poles and back to the mech. And then it would issue an alert through basically the 5G or the CVDX equipment that we had on the roadway wirelessly to either the pedestrian board or to the vehicle HMI that I will show in a second. So this is the lighting boards, as you can see. So this is the video on the left, or picture on the left is taken from an aerial view to show how bright the board is. And then we have red and green based on whether or not it's safe to cross. And then we have a video here. I don't know if you'll be able to hear the sound or not. Let's see if I can play it.
Yeah, the sound happens at the end, I believe. So part of the feedback that we got also allow us to create different patterns. So it was not only solid colors, that actually blind color people can actually notice those patterns when they are doing the, a lane crossing or go through the crosswalk. So this system have the ability to create and change colors, as also be flexible on generating different patterns like arrows or strip lines as needed.
Okay. And then we've got our in-vehicle HMI was a small display mounted via a tablet holder in the cup holder of the vehicle. Yeah, just a small display that would show either of the two alerts on the right, depending on whether or not there was a person detected in the intersection as you approach, or if there was another vehicle detected in the intersection as you approach. Right, and so this all leads us to our scenario testing. So there were 6 use cases that were provided by NEC that we used to evaluate the 5G deployment and the edge compute capabilities. So the 6 use cases were specifically collision prediction, street notification or street parking notification, traffic accident detection, so post-accident. So if something were to happen and maybe the camera wasn't visible at the time, and then you swivel your camera back over, can you now detect that there's an accident and issue alerts for that? We had pedestrian crossing detection, right and left turn detections, and overspeeding detection. So we'll go through these one at a time and look at our kind of KPIs for each of these that were given by the sponsor. So basically for the collision prediction, we wanted to go from predicting a collision to displaying it on the tablet in the car with less than 1 second latency. So that's about 6 meters if you're traveling at 15 miles per hour. We were aiming for greater than or equal to 80% detection rate across all of our tests. For street parking notification, we were looking at the same 1 second latency after detecting the street parking. We wanted to be able to detect this behavior within 40 meters of the camera, and then add a detection rate of 80%. And then I'm also, maybe it's hard to see, but these are little diagrams just indicating where the vehicles are, or what the scenario looks like. For traffic accident detection, we're again looking for 1 second after occurrence, then being able to detect it, and again, an 80% detection rate across our testing. For the pedestrian crossing detection, we wanted to be able to do, again, 1 second within 20 meters of any of the cameras, and then with an 80% detection rate. Right and left turn, same thing. So essentially being able to detect whether a vehicle was traveling straight through or it was going to make a left or right turn. And again, 1 second and 80% detection rate for that. And then overspeeding, same thing again. So if the vehicle's traveling through the intersection too quickly, we want to be able to detect that quickly and issue potential alerts if needed.
So those use cases scenarios basically were a brainstorming session between VTTI and the sponsor to understand what could be the needs between cities and DOTs for smart intersection technology. Those 6 scenarios were picked in trying to understand the more important alerting mechanisms that can be provided to the drivers and pedestrians, but also considering one of the sponsor features to detect a specific use cases that can be also useful from the implementation, commercialization side of things.
And so we performed a number of variations for each of those scenarios. So for instance, we would have pedestrians or vehicles crossing from every entrance to the intersection, multiple pedestrians, single pedestrians. We did bicycles, motorcycles, cars, trucks. Lots of different unique scenarios were performed, in 138 in total, often with multiple repetitions to assess kind of repeated, if the accuracy stayed the same, basically. We did have many scenarios involving collisions with pedestrians. These were ran with an AB Dynamics articulated pedestrian target, obviously for safety reasons. Normal vehicle scenarios were filmed kind of vehicles approaching and then stopping short at the intersection, without any actual collisions happening. All right. So we have results. JP, do you want to take over?
Sure. So part of the first testing that we did was trying to understand how this 5G network actually can provide ultra low latency, which was one of the main goals of the project. the BTTI Smart Road provides flexibility and also give us to the sponsor the ability to change the UEs or the user equipment placements. And we actually try to do different testings, but here are the best results that we were able to achieve. Uplink, which is the more critical one because we're uploading video and video analytics data to the MEC. It was around 123 Mbps. The downlink was also high, over 50 Mbps, 72.3 Mbps. And the round trip time of ping is 50 milliseconds average. That was from the UE1, and the UE number 2, which is the one located in each of the poles where the cameras were installed, have a little better performance because what we have been noticing was the line of sight between the UE number 2 and the RU were in better location. This also was useful for the sponsor to understand limitations and also how we can improve latency between and delays to understand those parameters when sending data from the PC boxes back to the Mac. Next slide. So in terms of all the use cases and scenarios that we run, there were 138. We provide and allocate priorities for specific use cases. The collision prediction and also pedestrian crossings were the more important for the sponsor and for BTTI because they involve threats to both the road users and actually provides the ability to understand how soon this system can detect or predict these kind of scenarios. The results were pretty positive. Most of the results were around the 100 detection. There is some minor tweaks due to the specific vehicle size and types. For example, for the street parking notification, they were not as great as the other, but in overall, the system were able to detect all these 6 use cases and be able to warn the vehicle and pedestrian in all these situations. One of the things that we were also looking into here is how reliable was the alert mechanisms. So one thing is repetition; those were also executed, and they were actually over the 80% rate. But BTTI worked with the sponsor to provide what will be the best time to collision or distance to actually trigger those alerts. The sponsor do not have too much experience about those parameters, but they were able to tweak those based on our feedback. They actually make the best of these alerts generated to the user in the vehicle or on the intersection at the crosswalk. Next slide, please. Here is also the system latency that we perform using time stamping from the camera all the way to the OBU units and HMI. And so, as you know, the blue side of things is pretty much the sponsor infrastructure that they deploy. And we were able to check the average time delay between one packet to get to the MEC, which is the server that process all the video analytics and generate the alerts, was around 144 milliseconds. And from there, back to the OBU and the HMI, they were at an additional 206 milliseconds. One of the challenges that we fixed along the project was the time synchronization. Different subsystems were not synchronized, or they were using different sources. We were using, BTTI was using NTP, while some of the servers and MEC were using GPS. So where we were able to align those times using a common source, and that actually helped us to understand this delay generation. On the CV2X, as you can see, there is a considerable 141 milliseconds, and one of the reasons, and that was part of the improvement that we request to the sponsor, was the amount of packets generated every second. We were receiving more than 5,000 packets per second. They need to be broadcasted or forwarded to the RSU. So we implemented filtering and also detect for specific use cases that were detected in order to reduce this bandwidth between the private 5G network and the CV2X network. Also, the CV2X uses security itself by using or signing the packets that are being transmitted from the RSU to the OBU. The RSU is the roadside unit that is mounted at the intersection, and the OBU units are the portable units. They are installed in the vehicle and also on our HMI pedestrian board as well. These OBUs decodes the message, verifies it's signed properly, and provides that to the HMI embedded platform to trigger the alert, to play the sound, or show an image based on the use case. So here there was also a good opportunity for improvement, but the 350 milliseconds is still valid to notify the user and also driver or pedestrian about a threat or a scenario that can be affecting in overall the traffic intersection. So we believe this is a very good deployment in terms of the latency itself. However, we would like to, in this second phase that is happening currently with this sponsor, we have been reducing these 350 milliseconds to actually 100 milliseconds in average. We've taken place the feedback that we found from phase 1, and we already executed on phase 2. Also, the BTTI conduct a review of few of the scenes that needs to be adjusted for a real deployment. This is a proof of concept, obviously, but the sponsor is very interested in knowing what needs to be done to move this implementation back to a real intersection, right? So we went through the hardware perspective. We need to reduce the footprint. The computers, the PC boxes needs to be reduced to actually allow us to put that in a cabinet at the intersection. But also in terms of software and ability to access the data in real time, we provide some feedback about implementing APIs or external access. So DOTs or cities using these kind of solutions can review what is happening on the intersection, like checking how many events have been detected, if there is any incidents or predictions detected, and also how many alerts were generated using the video analytics software. I will let Marty also to complement.
I think you covered most of the points. The only thing I have to add to that is, there's still a lot of work to do on assessing the HMI, actually, the appropriateness and effectiveness of it. We, like JP said, this is a proof of concept. We were really just trying to understand, get a kind of a reference implementation. How could you do this for both the pedestrian lighting board and speaker, and then the vehicle HMI as well. For a real production system, you would obviously need something integrated much better into the vehicle or into the environment itself. But I think this was a useful kind of exercise to see, how could that be done? How can we leverage these technologies to have really fast alerts and with pretty high accuracy implemented in the intersection. So yeah, I think that's all we have. And we're happy to take any questions from the audience now. I know we've already had some come through. I don't know if some of those have been answered already. Seems like JP's been busy in the chat.
Yeah, I think that those have been addressed. But Marty, I saw that, you were kind of saying that it's a good beginning point in saying like how these things could be addressed in the future. But what are the challenges that you're seeing might happen if these private 5G technology is transferred and installed on real traffic intersections off the smart road? What do you see?
I think one thing we noticed is we were seeing at least initially a lot of false positives with the system, and so that's definitely a real concern. Dealing with close calls or things that you don't really need to alert for, and how do you filter out kind of the definite you need to alert for this versus the you might not need to alert for this. Sometimes it's really hard to tell, and with the kind of margins you're dealing with in these kind of situations where 1 second can be the difference between hitting a pedestrian or not. It's really a hard call to make. So that's going to be a real challenge, certainly for everyone moving forward. I don't know if you have anything to add to that, JP, maybe from an infrastructure side.
Yeah, from the infrastructure side, well, the systems were running Windows, for example, and they require user interaction. One
I think we lost him, Marty. Do you know what he was going to say?
I think basically.
And also,
hey, JP,
yeah.
Sorry, you caught up. So if you're going to have to start again, we didn't hear anything.
Okay. I was saying that. Can you hear me now?
Yes. Mm-hmm.
Okay. So what I'm saying is that we suggest the human interaction and requirements for bringing the private 5G and all the computing hardware platforms up and running requires a lot of interaction. That have been addressed on the phase 2, but still there is few things that needs to be maybe converted, like the operating system, the way the sequence is happening in terms of how you power up a private 5G. We learn how complex is the setup, but also we provide suggestions how we can programmatically enable each of the subsystems in order that they don't require a person to be on site to just open the box and press a button. So those things are minor details, but actually allows for a real deployment and reduce the time to the system bring up and running.
Okay. We have a question from Colin. How often would calibration, if this was actually deployed, how often would calibration of the camera sensors be needed? And are there alternatives to the use of stationary boxes at the intersection?
That's a good question. And actually, that was our concern for real intersection deployments about that specific item. I believe the sponsor, part of his initial proof of concept, used a LiDAR to put on boxes to actually measure the distances. However, in this second phase, they have been maturing in this aspect by not requiring to do any calibration, but adjusting the pixel to distance or calculation and transformation. So they are already aware that, in a real deployment, they are not going to have a chance to put boxes in the intersection, obviously. So they're having other techniques to do that calibration or pre-calibrate the cameras before they are going to be installed in a real intersection.
Yeah, and I think another way to it's possible to do that is to find. You basically need to find a ground truth common point between the camera and some known other coordinate system. So, for instance, you could find known points of GPS in the intersection and find the pixel that they are in the camera that they both reference to, and then you can, from that, you can predict the GPS coordinate from the camera view as well. That's another technique to do this. But the main thing is you need known points in all the reference frames. So in your real world reference frame, and then also in the camera reference frame as well.
Right. I have another question, Marty. You said, 1 second does make a big difference in decision making for pedestrians and saving lives and not. So does the private 5G latency, is it good enough to warn pedestrians at vehicles and to be able to avoid those fatalities and accidents?
It's a difficult question. I think without doing some human testing, it's going to be difficult to say. So that's kind of what I meant in my last point, that actually understanding the effectiveness of these systems requires a little bit more than just the technology side, and it requires doing testing with people and putting them in the situation and seeing how they react. to these specific types of alerts, and whether or not the alerts that we've developed or that have already been developed are effective enough in getting their attention and causing the right behavior at the right time. So yeah, it's hard to say. The latency is pretty good. I mean, 350 milliseconds for some of the, that was only on average. For some of the alerts and that kind of thing, we were seeing shorter. And then as JP mentioned, so with phase 2, we're trying to get that down to 100 milliseconds. And at that realm, I think it's probably safe to say that it's not a hindrance, at least the time of the system. The timing of the system isn't going to be a problem at that point.
And obviously, there is other scenarios, for example, where it might be more challenging to the system to detect runners. For example, they come to the intersection and they just run away. It's difficult for the system to maybe doing some tracking or generate some warnings for them. Or any other scenarios that we're actually working on this second phase is wild animal detection and people falling around the intersection. These additional scenarios are enhancing their capabilities. However, as Marty said, part of our research is limited to safety evaluation, so we cannot expose humans to do this kind of scenarios, or even have, for example, simulate a collision. The way we did it was very specific, using video or even doing at low speeds. However, the sponsor is looking into alternative or other ways to do that on their side of things in their Japanese test track as well. So we cannot fully test the system, but the next step that they are looking is into getting an approval for a real deployment where more data they can actually process and actually inject it into their machine vision and video analytics software. They can be actually able to detect and review those scenarios and confirm if the latency and the detection metrics are good.
Okay. We have another question about system latency. You might want to go in the chat box and read it yourself, but for everybody, I will go ahead and read it. Colin asks if he's reading the chart right, thinking that if only V2X communications were used, the latency would have been 65 milliseconds and the 116 milliseconds from the edge servers versus the 350 milliseconds for the full system. Is that correct?
Clarify that. 65 seconds is the time that the RSU sends the message from the infrastructure to the vehicle or to the pedestrian HMI board. Those 65 milliseconds include the signature of the message, the encoding on the RSU, and the decoding on the OBU. But before that, to actually know when there is an alert or a scenario detected, that's all the time that you see in the back is the time that it takes the camera, the MEC, the 5G to process a frame and detect there is a collision or there is a use case scenario detected. And that covers the entire 350 milliseconds total.
I think he might be asking specifically if it's possible to use only the edge server to do all the processing and then put that into from the RSU to the OBU, and then is that a way to reduce the total system latency by quite a lot?
Well, that could be possible if you have only one camera. If you have one camera, the edge server can actually generate the metrics directly to the CV2X RSU. However, in this deployment, we are using 4 cameras. They need to be integrated into the MEC server, which is the centralized computing platform. They actually process the data coming from each of the cameras, edge server metrics, and it generates also all the detection alerts. They are going to be forwarded to the CV2X RSU. So in theory, yes, it should be able to reduce that latency. However, that should work only for one single camera system. And here, what we are trying to test is how a multi-camera subsystem within a private 5G network can actually detect different angles of the intersection, but covering different use cases as well.
I think you mean one pole of the intersection, right? Because you could integrate two cameras into one edge server, but you can't do it between the two poles without running the lines between them, right?
Yes, that's
Right.
correct.
Yeah, part of the reason that the 5G is helpful for this is because you can communicate between the poles very fast without, especially and more cheaply than having to dig up the whole intersection and stop traffic for weeks to do that, to install a fiber line between them. That's part of the impetus for trying it this way is trying to avoid some of those costs and some of those kind of downtime you'd have in a normal intersection.
Understood. Thank you.
All right. Are there any other questions for Marty or JP before we close out? If you do have any questions, you can go ahead and keep typing, but I am going to go ahead and first thank you for joining the webinar today. This webinar is going to be uploaded onto YouTube, and as well, we'll have the slides available on the safety project site. If you've registered for this, which you obviously have since you're here, I will be sending out an email when those are available. It should be within the next week or so. You will look out for an email with those links. And also, registration is already open for our next webinar for next month. So next month's webinar is going to discuss the issues revolving around the use of automated shuttles and buses for non-able-bodied individuals. So in this coming up webinar, people will discuss the enhancements to vehicles, service operations, street systems, and built environments to ensure safe and equal access to automated shuttles and buses. And our next two webinars are kind of along those same lines. So we're kind of getting into a nice little topic there. The webinar is scheduled for March 28th at 2 o'clock. You can register on our website. You'll probably also get an email if you usually get those. And I also just dropped a link into the chat box if you want to go ahead and register for that one as well. All right. I'm going to leave this open, so people, if they're using that chat box or wanting to go ahead and register to get that link, you can go ahead. Otherwise, if there are no other questions, thank you, JP, thank you, Marty, and thank you all for attending, and hopefully we'll see you in March.
All right. Thanks, everyone.